Okay, so we're talking about the Runge-Kutta method, and we've got this picture here. And the idea again is that we're going to take several samples of the slope, and then we're hopefully going to be able to get some kind of weighted average in order to make that a more accurate solution. And so we'll just go ahead and start in then. K1 will be our first estimate, the usual. Now K2 is going to use this first estimate to figure out where I am here, and so K2 is going to be f of Tn plus h, comma, and then Yn plus h over 2, because I'm only taking a half step, plus h over 2, and then for my y value, let me try that again, Yn plus now h over 2, and then where am I going to go from here? I'm going to use K1 for that. Okay, and now K3 is going to be taking the same time step over, but now I'm going to use a different value of y, and the value of y I'm going to use in K3 is K2. So that's going to be Tn plus h over 2 again, and then Yn plus h over 2, and then it's going to be I'm going to use K2 instead of K1, right? And then finally K4 is taking the estimate out to Tn plus h now, all the way to the end, and then Yn plus h times K3. Okay, and so now I've got 4 estimates of my slope, and so the way I'm going to work y sub n plus 1 now is going to be Yn plus my step size times, and now I'm going to take a weighted average of the 4 slopes, so that's going to be, now the weights can take on different forms. Different algorithms will use different weightings of their estimates, and in Runge-Kutta we're going to have a weight of 2 for each. I'm having trouble with my eraser there. There we go. I'm erasing too much now. 2K2 plus 2K3 plus K4 divided by, let's see, that's 2, 4, 5, 6 divided by 6. Okay, so that's how I get my weighted average. Okay, and so that's not plus or minus, by the way, that's just a plus there. I better get it right. Good. So this is the Runge-Kutta algorithm. And the Runge-Kutta algorithm, the local truncation error is proportional to h to the 5th. So that's a huge increase in our error, right? So our decrease in our error. And then the global is proportional to h to the 4th, and so this is called a fourth order method. Now we could make this a third order method, or we could make a fifth order method. There's lots of different ways to do that, and so what happens is, how do I estimate? How do we estimate the step size if I don't have a step size estimation in hand? Well, the idea here is that you can use 2 methods. Let me say that differently here. We're using 2 methods. For example, we might use something that is using order 2 and order 3, and we can see by the difference of those 2 methods what an estimate of our error. Okay, and use to estimate the error. Okay, and so we'll have some kind of lower tolerance for our estimate, and if the error is too big, I'm leaving this open here on purpose. If the error is too big, cut the step size by some fraction. So for example, cut it by 1/2, so half the step size. Then run order 2 and order 3 again and see what the error is, and if it's too big, cut the step size. And so if you continue with that, you'll be able to, we can estimate the error this way, or estimate the step size. And so when we look at Matlab's algorithms, Matlab's built-in algorithms, we'll be using ODE 2.3. There's an ODE 4.5. This one is kind of the workhorse, I think. This one is using the Runge-Kutta order 4 and then another one order 5. But 2.3 actually works fine in a lot of cases, unless you have some reason to get a higher order. Sometimes the lower order is fine, and it gives you a lot faster results. Okay, but there's also like ODE, what is it, 1.5? Let me pause this for a second, I'll check. In fact, it's 1.5S is the one I'm thinking of, and the S here stands for stiff. And we won't talk about it in this video too much. I'll just say that stiff ODEs, you have to be careful with your method because they'll blow up on you fast if you're not careful. There's also an ODE, there's also a stiff version of ODE 2.3, ODE 2.3S. And then there's then there's other ones. There's ODE 2.3T for the moderately stiff differential equation. And so I guess the upshot there's like 6 or 7 of these solvers in Matlab. I would always start with ODE 2.3, and just, you might double check it with a higher order method like ODE 4.5, and just to see what kind of solutions you're getting. And if it looks like you're going to need something more in depth, then you might try the ODE 1.5S just to see. This is going to take a lot of work to, you can see, you're comparing order 1 to order 5, and so there's a lot of computation under the hood there. Yeah, so the way to use the solver, maybe I'll go ahead and just write down a sample problem, is to do the following. So suppose I want to just run a quick examples here. We just have a couple minutes left of this video. So suppose I want to solve y prime equals 2t. So it's a very simple differential equation with y of 0 equals 1 on the interval from 0 to 2. Okay, now I don't have to specify the step size here. So what I will do is first I need to define my function. So I'll say f is equal to at ty. And by the way, even though the differential equation only depends on t, in general you want to put both, the solver is going to want to put both a t and a y into your function, even though it's only 2 times t coming out. Okay, and then we'll go ahead and define our other variables or parameters that we're passing in. Y of 0 equals 1, semicolon, t0 equals 0, semicolon, t final, tf equals 2, semicolon. I think that's all we need. Then the command for Matlab is just ty equals ODE, and then choose your method 2, 3. The f comes first, and then the time span comes second, and our time span goes from t0 to tf, and then our initial value y0. That's it. Then Matlab will plot out your t and y so you can plot. And sometimes it's nice to see where it's evaluating, so use an O. That's an O, not a 0. An O and a dash. Okay, and then it'll plot things like this. Okay, and so that'll be, go ahead and try this out. It's on the PDF file as well. Okay, so my last video for this section will just be a few fast conversions, because all of these methods that we've talked about so far require you to have a first order differential equation. So in the next video we'll do conversions.